Hello, this is Mrs. Bentley, and I'm here to work with you on the Unit 4 test review with exponential functions. So if you take a look at numbers 1, 2, and 3, the instructions ask us to fill in the key characteristics of the exponential functions. So in number 1, we're given a graph, and I'm just going to add the arrows because we know the function is continuing to go on the right, it's approaching our asymptote at 0, and on the left, it's continuing as we go to negative infinity, it's continuing to go up to positive infinity. So in class, we talked about that when we have exponential functions, the domain will always be all real numbers, and our range is going to depend on our asymptote. So if you look, we have an asymptote at y equals 0. So we know our exponential function is coming down, it's curving, it's leveling out, and it's approaching 0. Now notice our function is staying above where y is 0. Everything is above where y equals 0. So our range is y is greater than 0. When we talk about in behavior, we look at our graph along the x-axis. So on our x-axis, as we're approaching negative infinity, our graph is going up to positive infinity. And on the x-axis, as we are approaching positive infinity, our graph is coming down, leveling out, and approaching our asymptote at 0. When we read a graph, we read our graph from left to right, and as our graph goes left to right, the graph is coming downhill, so this is a decreasing function. Okay, number 2, we're also given a graph. We're going to again add our arrows to indicate that this is continuing. Since this is an exponential function, we know our domain is all real numbers. Our range is going to depend on our asymptote. So again, if you notice the graph, the function does come down, it turns, and it levels out right where y equals 0. So our asymptote is at y equals 0. So our range for this function is y is greater than 0. Again, as we look at in behavior, we read this at first from our x-axis. So as x approaches negative infinity, so as we're going towards negative infinity on the x-axis, the function is coming down, it's leveling out, and it is approaching 0. On the right, as we read along the x-axis approaching positive infinity, our function is going up, also to positive infinity. Read your graph again from left to right. So as you read your graph from left to right, this graph is going uphill, so this is an increasing function. Now for number 3, we're given a table of values, and we can list these as discrete values. So if you notice, your x coordinates are going to just be the list here under your x. This is your domain. So our domain values are 0, 1, 2, 3, and 4. Just remember, if a domain value was to repeat, you would not write it twice to list the domain. Same thing for the range. The range is going to be all your y values for the function. So in this table, our range values are 2, 4, 8, 16, and 32. If you pay attention to the pattern in our x column, our values are increasing by 1, so plus 1, plus 1, plus 1, so the common difference is plus 1. Our range values are multiplying by 2, multiplying by 2, multiplying by 2. Notice your domain values are increasing, your y values are increasing, so this is an increasing function. Okay, so for number 4 and 5, we are evaluating the function. It's given to us in function notation. They're asking us to find f of negative 2, given f of x equals 4 to the x power. Remember, this is read f of x. So this is telling me that our x value equals negative 2. So when we evaluate this function, f of x equals 4 to the x power, we are going to write this as f of negative 2 equals 4 to the negative 2 power. 4 to the negative power equals 1/16. Or as a decimal, you could write this as decimal 0.625. Okay, for number 5, it says given the domain 0 to 5, find the range if f of x equals 3x minus 3 to the x power minus 2. So if we go into our y equals, I'm going to use my calculator this time since we are evaluating the function for 3 values. Remember, we can go into our table. We can type in the function at y equals. So we're going to type in this equation, 3 raised to the x power minus 2, and now hit second graph. So in our table of values, the first domain value we are evaluating the function for is when x equals 0, and when x equals 0, y equals negative 1. The next domain value we're evaluating the function for is 2, and when x equals 2, y equals 7. And our last one, when x equals 5, you'll see that y equals 241. Okay, for number 6 and number 7, we are going to graph each function and identify whether the function is representing exponential growth or decay. So go ahead and go back to your y equals. We're going to clear out the last equation. Let's go ahead and type in the new equation, 3 times 4.5, and raise that to the power of x. And let's get a table of values, so second graph. And let's see, I know this is not a very nice decimal to graph, but just notice that it's 0.14815, so that's just going to be barely above 0. So on your graph, if you go left 2, and then just up barely above the x-axis. So negative 1.6 repeating, you're going to go left 1, here's half, so we're just going to put it a little bit above the halfway mark. 0, 3, we're going to stay at 0 and go up 3. 1, 13.5, so write 1, and here's 13, so there's 13.5. And that's all that's going to fit on our graph. Now, if you scroll up through your table, you can see that our y values are approaching 0. So when you draw your function, you're going to draw the function to curve and begin approaching 0 right above the x-axis. Now, if we look at our function from left to right, this function is going uphill, so we know this is an increasing function. You can also look at your b value. Remember, if your b value is greater than 1, we know this function is exponential growth. Okay, for number 7, we're also graphing, so we're going to go back to our y equals, clear out our old function, and type in the new, so 5 times decimal 5, 0, and we're raising this to the power of x, and second graph. Okay, so right now I'm at negative 5,160. That's not going to fit. Our table goes up to 20. So the first point I see that's going to fit on our graph is negative 220. So from the origin, we're going to go left 2 and up 20. Negative 110, we're going to go left 1 and up 10. 0, 5, we stay at 0 and go up 5. 1, 2.5, so here's 1, and here's 2, so here's about 2.5. See if we have any more points that will fit. Here we have 2, here's 1, 1.25, and 3, write 3, and, okay, so this one also appears to be curving and approaching 0. Again, hit the graph on your calculator. Mine is zoomed in, so give this just a moment to finish, and I'll hit zoom 6 to get back to my standard window. And you can see that the function is turning and approaching 0. So draw the function to come down. It's going to start curving, and it's approaching the x-axis. So right here, where y equals 0, we're approaching 0. Now notice this graph is going a different direction. As we read this graph from left to right, the graph is turning and going downhill. Also pay attention to your b value. Notice that your b value is less than 1, but it's also greater than 0. So when your b value is greater than 0, less than 1, we have a decay function. Okay, so number 8 is asking us to explain how you know whether the function is exponential growth or decay. So let's say we're just given the equation. If we're only given the equation, remember we can look at the b value. And if b is greater than 1, we know the exponential function is growth. So that's going to be exponential growth. If b is between 0 and 1, so b is greater than 0, b is less than 1, we know the function is exponential decay. Now, if we had a graph, we could look at the direction our function is going in. So if our graph is going uphill from left to right, we know we have exponential growth. And if our graph is going downhill from left to right, we know we have exponential decay. Okay, and number 9, Anna's car was worth $25,000 when she purchased it. The value of the car depreciates at a rate of 9% per year. So remember, the information we're looking for is the starting amount or starting value. We're looking for the keyword that lets us know, is this exponential growth or exponential decay? And we also need to find our rate. Our rate is going to be a percent. We will need to convert the percent to a decimal. And if it's growth, add to 1. And if it's decay, subtract from 1. So I noticed Anna's car is originally worth $25,000, so that is going to be our starting value. I also noticed the word depreciate, so that tells us that her car value is going to decrease or decay. The percent is 9%. Remember, a percent, you can take and move your decimal 2 places to the left and then fill in that empty spot with 0. Or you can, on your calculator, take 9 and divide by 100, and you will also get decimal 09. Now, since it's depreciating, we will say 1 minus decimal 09. And then we're going to raise this to the number of years. So x represents the number of years. Now notice we can simplify our parentheses. 1 minus decimal 09. This will simplify to 25,000 times decimal 91. And we're going to raise to the number of years. So x again is representing years. So this is our exponential decay equation. For part A, it says how much is her car worth in 8 years. So now we're going to calculate this. So on our calculators, we're going to type in 25,000 and then times the decay factor, decimal 91. And they're asking for the value in 8 years, so we're going to raise this to the 8th power. So when her car is 8 years old, the value of the car is now approximately $11,756.31. For part B, it asks how much is her car worth in 2 years. So still using the same equation, but changing our exponent. So 25,000 times decimal 91, and now we're raising it to the 2nd power. So when her car is 2 years old, the value is approximately $20,702.50. Okay, for number 10, it says a bank account that starts with $9,000 and accrues 3.5% interest yearly. How much money is in the account after 5 years? So I see that the account starts with $9,000, so that is our value for A. And this is our rate, that's our rate, our percent. And the word accrues, that means increases. So for this question, we need to use our exponential growth equation. So we're going to say y equals 9,000 times 1 plus. And remember, we need to take the percent, 3.5%, and move the decimal 2 places to the left. Or again, on your calculators, you can do 3.5 out of 100, and that's also going to give you that decimal 0.35. Very important, the 0 is between the decimal and the 3. And they're wanting us to calculate how much money is in the account in 5 years. So the exponent will be 5. So we could simplify this to 9,000 times 1.035 raised to the 5th power. So 9,000 times 1.035. Just double check how you're typing it in. And now we're raising this to the 5th power. And so in 5 years, the account will have approximately $10,689. And remember, we're rounding to the nearest cent for money, so the 6 will round to 7 to an 8, so that's going to be 18 cents. Okay, and number 11, the sequence shows the number of Christmas trees and nursery plants each year. So we're given a pattern, 200, 100, 500, 25. The question asks, which formula can be used to determine the number of trees the nursery will plant next year, if the number of trees planted this year now is known. So we need to identify what type of sequence we have and what type of pattern. So if I initially check addition and subtraction, 200 minus 100 is 100. But notice 100 minus 100 should be 0, and this is 50. So this is not an arithmetic sequence. Okay, so now I notice the numbers are getting smaller. So if I'm multiplying times a number less than 1. So if you think about the relationship of 100 to 200, 100 is half of 200. 50 is half of 100. 25 is half of 50. So we are multiplying by 1/2 each time. So we learned that we can write the recursive equation as next equals now times 1/2. We can also write this in sequence notation, which is, notice the answer choices are written using sequence notation. So when we rewrite this in sequence notation, the word next is just going to be a sub n plus 1 equals now a sub n times 1/2. So if we look at our answer choices, this is 2 times, this is 2 times plus 6, and now b is 1/2 times a sub n. So B is the correct answer. They have the order a little different, but that's okay with multiplication. So our correct answer is B. For number 12, a student claims that the next term of the arithmetic sequence, 0 through 6, is 12. What error did the student make? So we know arithmetic sequences need to either have an addition or what can appear to be a subtraction. It's just adding a negative number, and we're given 0 through 6. So I see that it's increasing, so we're adding. So 0 to 3, we're adding 3. 3 to 6, we're adding 3. So if we continue this, 6 plus 3, the next term should be 9. This student claimed that the number was 12. And the question asks us to identify what error did the student make. So it appears that maybe the student multiplied by 2 instead of adding 3. Because notice if we multiply 6 times 2, 6 times 2 is 12. 3 times 2 is 6. So they thought this is a geometric sequence, but it's an arithmetic sequence. Okay, for number 13, we are asked to write a recursive formula for the sequence. So remember, recursive, think of that root word recur. We're just talking about what's that recurring pattern from one term to the next term. So from 13 to 22, we are adding, and again, if you can't see this pattern, remember we can work backwards. So I see it, but I'm just going to model this for you guys. So again, if you aren't sure what we're adding each time, start at the end of the sequence and work backwards. So 49 minus 40, that's 9. 40 minus 31, that's also 9. 31 minus 22, 9. 22 minus 13, 9. So we notice that the pattern is plus 9. Okay, so since it's recursive, we can say next equals now plus 9, or in sequence notation, a sub n plus 1 equals a sub n plus 9. In number 14, given the first term equals 7 and the formula, remember this just means the next term in the sequence equals the now term minus 9. Find the first 4 terms. Now they're giving us the first term, so we know our first term is 7. The rule is to subtract 9. So if we take our 7 and say 7 minus 9, the next term is negative 2 minus 9, negative 11, minus 9, negative 20. So we need to understand how the next equals now equation looks in sequence notation form. Again, this is just next equals now minus 9. And if we know the first term, we can repeat the pattern over and over to find additional terms in the sequence. Okay, 15. Given the arithmetic sequence 5, 14, 23, 32, write an explicit formula for the sequence. So the explicit formula, since it's arithmetic, is going to be a linear equation. So we can use our y equals mx plus b, or we can use the sequence notation, the a sub n equals the common difference times the number of the term in the sequence we're looking for plus the 0 term, a sub 0. These two equations will work the same way, so pick the equation you feel comfortable with. We have to identify the pattern. The pattern is either going to be your slope or your common difference. So from 5 to 14, that is an increase of plus 9, 14 to 23, plus 9, 23 to 32, plus 9. Now, to find the y-intercept, we need to work the sequence backwards. So our first term is 5. So remember, you can think of this as like a table. This is your first term, your second term, your third term, your fourth term. We're trying to find what the term in front of the first term, the 0 term, would be. So what's 5 minus 9? That's going to give us negative 4. So our a sub 0, or we could say our b value, our y-intercept, equals negative 4. So we now know that the common difference, or the slope, is 9, and we know the 0 term, or the y-intercept, is negative 4. So the equation is y equals 9x minus 4. Now for 15a, they want us to find the 25th term, and now that we have the equation, we can just substitute 25 in for x. So on our calculators, or in your head, we are going to say 9 times 25, and that equals 225, and now subtract 4. So this comes out to 221. For 15b, we're asked to find the 100th term. Same process. Now we're substituting in 100 for x, and 9 times 100 we know is 900. And then 900 minus 4, you should get 896. For number 16, we're given another sequence. So it says, given the sequence -4, -20, -100, -500, -2500. Find the next term. So I notice these numbers are getting they're getting smaller since they're negatives very quickly. There's a big difference from -4 to -2500. So I suspect this is a geometric sequence. So I'm going to test that first. So, what could I multiply -4 by to get -20? Okay, that would be +5. Remember, a negative times a positive gives us a negative. -20 times +5 is -100. -100 times +5 is -500. So we have found the pattern. So we know the pattern is multiplying by 5. Now this asks us to find the next term. So if we take the -2500, which was the last term given in the sequence, and multiply that times 5, we know our next term is -12,500. Okay, for 16a, what is the common ratio? Again, the common ratio is the pattern. So our common ratio is 5. Now we're asked to write a function rule in the explicit formula for the sequence. So I'm just going to use my exponential equation, y equals a times b raised to the x power. Remember, b is your pattern, and a is your y-intercept. So again, a y-intercept is what y equals when x is 0. So we know that our pattern is 5, so we know our b value equals 5. And now if we take and work backwards, because in a table of values, this will be our first term, our second term, our third term, our fourth term, and our fifth term. So our 0 term would come before the 1. So instead of multiplying by 5, we're going to take -4 and divide by 5. Now you could say that a equals -4/5, that's fine. Or if you prefer a decimal, -4 divided by 5 is -8. And now to write the equation, we're going to say y equals, again you could use the fraction or the decimal, I think most of you prefer decimals, so you can use the decimal, -8. And then times the common ratio of 5 raised to the x power. And remember, x is just the term number in the sequence. So for part 16c, we are asked to find the 11th term. So we're going to use the equation from 16b, and in the place of x, we're substituting in 11. So -8 times 5, raising this to the 11th power. And that's small because it's negative, but that's -3,906,2,500. Now I'm going to add my commas in. So that's -39,062,500. Okay, number 17 says, suppose a population of 75 crickets doubles in size every year. How many crickets will there be after 4 years? So remember, the starting amount is going to be our a value. This is going to be an exponential function because it's a multiplying rule. We're doubling. So remember, doubles means to multiply by 2. So our starting number is 75 crickets, and we're doubling it. So our b value is times 2. And we're wanting to know the number of crickets in 4 years. And I'm going to calculate this. So 75 times 2 raised to the 4th power. And this is 1,200 crickets. We'll have 1,200 crickets in 4 years if this population continues to double yearly. Okay, for number 18, it says the value of a $1,600 four-wheeler decreases 9% annually. What will be the value of this should say four-wheeler also, so I'm just going to change this real quick. Four-wheeler and four-wheeler. Okay, so I see the word decreases, so this is going to be decay, and the starting value of the four-wheeler is $1,600, and it's decreasing by 9%. We want to know the value in 6 years. So your equation is going to be y equals 1,600 times 1 minus decimal 0.9 raised to the 6th power. And if you want to simplify this before you calculate, that's fine. 1 minus decimal 0.9 is decimal 9.1, and then raised to the 6th power. So 1,600 times decimal 9.1, and then raised to the 6th power equals, this is money, so we'll round to the nearest cent. The four-wheeler is going to be worth $908.59. Now for part B, this one's a little differently, and I've shown you guys how you can do this using your graphing calculators by graphing the equation and looking at your table, or you could just go through and kind of test this out. We know 6 years, the four-wheeler is $908. So we're going to have to keep increasing the number of years until we see the value fall less than $400. So you could guess and check, that is an option, or you can type the equation into your graphing calculator at y equals. So you go to y equals, fill out the equation that's in your calculators, and we're going to type in the 1,600 times decimal 9.1, and we're going to raise it to the x power, because that's what we're trying to find. We're trying to find how many years it will take to for the value to fall less than $400. So now let's hit second graph, and we get into our positive. So right here at 0 years, this is the starting value of the four-wheeler, and you'll see the price beginning to drop. And we're looking for the first time it falls less than $400. Getting close. So it's going to take 15 years, somewhere between the 14th and the 15th year, but we're going to use the 15th year because when the four-wheeler is 15 years old, the value is now $388.81. So our answer for part B is 15 years. Okay, for number 19, it says graph of f of x equals 2x, and it's 2 to the x power. I'm sorry, I keep saying 2x, so it's 2 raised to the x power. It asks us to use the graph to the left. Now we have a coordinate plane, but there's no graph, so we're going to have to create the graph first. So we're going to go back into y equals, and we're going to type in the function 2 raised to the x power. And to get to the table of values, you're going to hit second graph, and we need to scroll back up. Okay, so here is where x equals 0. And when x equals 0, y equals 1. We have 1, 2, so right 1, up 2. 3, 8, so right 3 and up 8. And I'm going to try to find a few points going onto the left side of the graph. So let's scroll up into our negatives. So when x is -1, our y value is 0.5 or 1/2. And when x is -2, our y value is 0.25 or 1/4. So it appears this function is approaching 0. You can scroll up and you can kind of see our y values change. And notice the y values are getting closer to 0. So this function is going to come down, it's going to turn, and it's going to level out right above the x-axis. So now, using the graph to the left, find the value of f of 3. So here is where, remember this is red, f of x. So we're saying that x equals 3, and when x equals 3, here's the point, follow it over to your y-axis, your y value equals 8. Or, you can also refer to your table on your graphing calculator. When x equals 3, y also equals 8. In 19b, what is the y-intercept? So I can also look at the graph I've drawn, and remember the y-intercept is the ordered pair where the function crosses the y-axis. So our y-intercept is at 0, 1. What is the asymptote? Well, we said the graph is coming down, it's curving and leveling out right above the x-axis, so our asymptote is that horizontal line, y equals 0. It's very important you write this as an equation because it is a line, and we read the graph from left to right. This function is going uphill left to right, so this is an increasing function. Okay, last problem. Number 20. Suppose you deposited $1,235 you earned from a summer job into a savings account that pays 2.8% interest compounded annually. How much will you have saved in 7 years? So this is something that could really apply to you guys. You may get a summer job, you may decide to put it all into savings, and depending on what interest rate you get and how long you leave the money in that account, you will see your money show an increase or some growth. So the account is starting with $1,235, so that is our A value. It pays, so that's telling us it's going to increase. 2.8% as a decimal is going to be decimal 0 to 8 because I'm moving my decimals 2 places to the left. And we're checking for 7 years. So our exponent x is going to equal 7. So the equation is going to be y equals $1,235 times 1 plus decimal 0 to 8, and we're raising it to the 7th power. So if I simplify this, this is 1,235 times 1 decimal 0 to 8 to the 7th power. Okay, so 1,235 times 1 decimal 0 to 8, and we are raising this to the 7th power. So in 7 years, your account would have $1,498, and we'll round that to 37 cents. Good luck on your test tomorrow. Thank you. This has been Mrs. Bentley with help on your Unit 4 Exponential Functions test review.